This section is about the limits of functions. What we mean by a limit of a function in formal way indeed. So the main objectives of this sections, we expect from you after finishing this section to be able to understand and to define the limit. Intuitive definition, because this is informal. The formal definition of the limit will be in 2.4, inshallah. Also, we will study the one-sided limits when we have limit from the right and from the left. Also, the infinite limits when the limit of a function goes to infinity. And finally, the vertical asymptotes, and they are related to the infinite limits. When you have infinite limits, you have vertical asymptotes. If you remember in 2.1, we have studied the tangent problem. In the tangent problem, we have realized that the slopes, the limits of the slopes of the secant lines will be the slope of the tangent lines. Look at this function, for example. What will happen when x is around 2, about 2, near 2? For example, when it is 2.1, 1.9, and so on. As you can see, this function is a polynomial. It is quadratic function. So it is not that difficult. It is easy. It is continuous. It is defined everywhere because the domain of this function is all the real numbers. If you make a table of values for values close from 2, you can see that when x is going to approach 2, the value of the function is going to approach 4. It is almost 4. Here also, when you are close from 2, this also will be close from 4. The difference here that here x is greater than 2. Here x is less than 2. So the values here are greater than 2. The values there are less than 2. By the way, if you look what is 4, you can see that it is the value of the function. The value of the function at 2. It will be 4 minus 2 plus 2. It will be 4. So in this case, the approaching when x is so close from 2, the value of the function will be close from f of 2. Look, if you sketch the graph of this function is parabola, so it is not difficult to be sketched. So this is the graph of the parabola. When x approaching 2 with values greater than 2 or with values less than 2. You can see that the value of y, when you are on the y-axis, they are approaching 4. They will be close from 4. In fact, they are exactly 4. When it is exactly 2, it is exactly 4. This is what we can say that the limit, we will say that the limit of this function, when x is so close from 2, it will be equals to 4. And in a formal way, we can think about the limits like this. If we have a function that is defined near a value a, when you have a number a, and it is defined around it, not necessarily, by the way, it is not necessarily to be defined at a. F of a could be exist or does not exist. F can be defined or not defined at a, no problem. So it is not important to have it defined in the case of limits. So then the limit of the function when x approaching a, it will be equals to L. You can read it like this. The limit of f of x as x approaches a equals to L. Also, you can write it in another notation. F of x approaches L as x approaches a. It is another way of expressing this. You can write it this way or this way, but usually we will focus on this one. So you should understand, Shabab, that limit of x when x approaching a is L. It means that f of x need not even to be defined when x equals a. It is not necessarily to have f of a. If we have, it's okay. If this one equals to f of a, we have what is called continuous. The function in this case will be continuous, but it is not necessarily in the case of limits. So we could have it defined or undefined at a. The only thing that matters here is how it behaves near a. Look at these examples. The function here what is the limit of the function when x approaching a يا شباب? What is the limit? It is L.
L.
Now, the limit of the function here, it is L. And you can see also that f of a, it is the same as f of a. The value of the function at a, it is L. Look here. The limit when x approaching a from the right or from the left, the y value approaching what? It is approaching L. But here, look what is f of a. What is f of a? It is not L. This is f of a. Hey, this is what you have here. It is f of a. So f of a here, in this case, it is not L. It is not the limit. In this case, f of a does not equals to the limit of the function when x approaching a. Let's take another example. What is the limit here? The limit is L also. When x approaching a from the left or from the right, they will be closely, almost they will be approaching L. But what is the value of the function at a? What is f of a?
Does not exist.
We don't know. We don't know anything about it. It is a hole. There is a hole here. Look, the open circle here means that it is not defined at a. We were able here to define it, but here we don't know exactly what is it. So it is undefined. It is undefined. We don't know what is it. Okay. Now let's go to the first example. By the way, this is not a new example. Do you remember 2.1? This is similar to what we did in 2.1, but of course it was there x squared minus 1 over x minus 1. It is the same idea. Look, here you don't know. Let's assume that in this section we will just learn how to understand the meaning of the limits. So if you don't know how to do that, you can choose some values close from 1, like these values, and investigate the behavior. If you look at the behavior of the function, when the function is approaching 1, you can see that the function is approaching a half. This is 0.5. This is 0.5. So it is a half. So this means that this limit is approaching to a half. Of course, you will not use the calculator every time to do that. Just this is for you to understand the meaning of approaching, the meaning of the limits. So we can say that the limit of this function is 0.5. And if you look at the figure, you are not supposed to sketch the graph. If you don't know how to sketch the graph, it is not a problem. If you can, it will be okay. So when x approaching 1 from the right or from the left, the value of the function is very close from a half. Another example, which is the same, by the way. If you look, it is the same function that we were having here. But the difference now will be what? That this function is not defined at 1. But this function, it is defined at 1. When x is 1, this is, by the way, called piecewise defined function. So this is the value of the function when x is not 1. And when it is 1, the value of the function is 2. So this means that the value of the function at 2, it is equal, at 1, it is equals to 2. So g here, the function g, it is still having the same limit. But of course, it will not be equals now. The limit does not equals to the value of the function at 1. And this function, such function, we will call it discontinuous. It is not continuous at 1. Look, here is the definition. The value of the function, this is the meaning of that f of g, it is g, that g at 1 is 2. The value of the function at 1, it is 2. Another example here, here we are just estimating, ya shabab. We are not now learning how to evaluate. We will do this again in 2.3. In section 2.3, we will learn how to do that. But this is just to show you how you can estimate the limits and what are the problems that may happen when you use the calculator to estimate the limits. Look, if you use the calculator, what you can see here, if x is approaching 0, so you will start from 1, 0.5, 0.1, 0.05, 0.01, and so on. If you also look at this, it will be 1 point. The value of the expression will be 0.1666. It is it is irrational. It is rational number that is repeated. So you can guess that this is, by the way, it is just 1 over 6. So you can see that if you use these values, you can guess that it is close from 0.6. But if you use another values, look, when you use more small values, when you are so close from 0, look, if you use 0.00000.1, what you can see, the value of the limit is 0. So now you need to ask yourself, does this mean that the answer is 0 or 1 over 6? Which answer is correct? Is this or this? You will be confused. You cannot decide if you have such case. So this is why the numerical calculation is not always accurate. You need to use algebra to be sure 100% about the limit. So indeed, the value of the limit, it is 1 over 6, as we will see in the next section. We will see that in 2.3, ya shabab. So what is the problem? What happened? The problem is sometimes the calculator gave some false values. Why they give some false values here, for example? The reason here, for example, because when you get very close from 0, this will be very close from 3, and this will be 0 over 0, and this will confuse the calculator. So this is what will happen when you're so close to 0. And what we will have as a case that is 0 over 0, that is, of course, sometimes will not be accurate when you use your calculator. Now, in fact, if you want to learn further about these kind of problems, you can search for this in the website for further explanation about this, about the calculator's error. So we will not use calculator always. Of course, you can use it just to check sometimes. Another way here, this is important. We will prove this later. But how to guess the value of this function? Again, you need a calculator. And it looks like when you are close, very close from 1, this will be very close. When this is going to 0, this will be close from what, ya shabab?
1.
Almost 1.
Yeah.
And we will see that later, of course, that the limit of this function is 1. And it is a fact. It is a theorem. We will prove it geometrically in the next section. We will prove it in chapter 3, indeed. Not here, in chapter 3, not in chapter 2. This is the graph. If you have a graphing calculator, also you can sketch the graph like this. It is not easy to graph it manually. So look what happened. It is not defined at 0. If you put 0, you have a 0 in the denominator, so it cannot be defined at 0. But when x approaching 0 from the right or from the left, the value of the function will approaching, or the limit of the function will approaching 1. Okay, this is another example about when the calculators cannot help. This, of course, if you try to use your calculator, you will be in trouble to approximate or to estimate the value of this limit. Now, what is the problem? The problem when you put x equals 0 here, it will be sine pi over 0, almost 0. And this is undefined. How can you define it? So what you will say, some of you, they say, oh, the limit does not exist. There is no limit. No, there is a limit for this function. Sorry, there is no limit for this function. So how to guarantee that the limit, for example, this function sine pi over x, we will see now that the limit does not exist. But if you multiply it just by sine, for example, by x, for example, like this, the limit exists for such kind of functions. We will see that later, of course, in 2.3, that this type of limits, this indeed, the limit will be 0. And for this one, it does not exist. We will see why and what is happening exactly. Now, to see that, I will skip the details of the calculations or of the numerical calculations. No need for that. Just what you need to know at the beginning, that it is not defined at 0. And if you have a graph, if you sketch the graph of this function, look how it will behave near 0. This is sine pi over x. This is the function. when you are so close from 0, look what happened to the function. It start isolating. It is going like this rapidly. You don't know when you are, for example, let me give you some examples. It will keep isolating between -1 and 1, and you know that sine of any theta, it is always between 1 and -1. Always. It will not go over 1 or below -1. So, for example, look at f at 0.1, it is 0. F of 0.01, it is 0. If you take another value, for example, 2 over 101, you will see that the value of the function is 1. So sometimes it will be 0, sometimes it will be 1, sometimes it will be a half. So it will be isolating between -1 and 1. It will be, it can take any value. But when you are so close from 0. So what we will conclude from that, and we will see that this type of function does not exist, because for any limit to exist, it should have one limit, not infinite limit. Let me, if you want to, another example about using the calculators to estimate, look also at example 5, where the limits of such functions like this exist. Now, I think it is time, this example tell us that look at the limits when they are different from the right and from the left, and you cannot decide which limit exactly. The second part of this section is the limits from the right and limits from the left. So the best example about the one-sided limits is the Heaviside function. The Heaviside function, by the way, it is a function that is 0 for all the negative values and 1 for all the non-negative values. And the graph of it like this. For any t greater than 0, it will be 1 or equal 0. And for any t less than 0, it will be 0. In fact, this function is named after electrical engineer. The people of electrical engineering, by the way, they have many contributions in mathematics. Heaviside and Fourier are one of the greatest electrical engineers in mathematics. Look here at t approaching 0 from the left, the value of the function approaching 0. When x approaching 0 from the left, when you are going like this, the function approaching 0. Y is 0, here it is, the green one, the blue one. Now when t approaching 0 from the right, y approaching 1, so it will approach 1, the value of the function will approach 1. So we will express these statements like this. Simply, instead of writing this as t approaching 0 from the left, h of t approaching 0, we will write it simply like this. Limit h of t when t goes to 0 minus this minus here, or we will read it from the left. It means that t, it is less than 0. This is the meaning of that. If you have the another one, when t approaching 0 from the right, we will write it 0 plus. And by 0 plus, we need that t is greater than 0. When we say t goes to 0 from the left, it means that the values of t are less than 0. When t goes to 0 from the right, it means that the values of t are greater than t. I think, yes, I mentioned it here also. It is also written here for you to revise it if you want any time to understand the meaning of that. Now, let's define the limits when x, the one-sided limit. Similarly, by the same way that we defined before, the limit of the function when x approaching a from the left, you can read this as this, by the way, the left hand limit of x as x approaching a from the left is equals to L. Okay? x here it is less than a. Yes.
تقدر تعيد بس النقطة اللي قلت فيها الموجب والسالب نحطهم.
We will repeat it here, no problem, don't worry. Now, what is the meaning of x goes to a from the left? It means that the values of x are less than a. Like here, look, this is a. So when we say from the left, we mean that x will approaching a from the left with values less than a. When we say that approaching, look here, when we say that x are approaching a from the right, we will write it as a plus, like this, a plus, but we read it a from the left. When x approaches a from the right, it means that x is getting close from a, but it is greater than a. As we did here, ya shabab, this is the purpose of these numerical examples. If you notice, ya shabab, here, for example, let me give you another clear one. If you look here, x here, it is less than 1. So it is 0.5, 0.9, 0.999. So here x is approaching 1 from the left. Here x is greater than 1, 1.5, 1.1, 1.01, and so on. Here, in this case, we have x approaching 1 from the left, from the right. Is it clear now? So this is the meaning of approaching from the left and right. Now, again, this is the notation. This is the limits from the right. And these are the left, the meaning of them. Graphically, it is clear here. When you have a, this is the x-axis. This is a. Here, approaching from the right. So we will write limit. Here we will write it as limit when x approaching a from the right. Here, when it is approaching from the left, we will write it as x approaching a from the left. Okay, why it is important talking about the limits from the right and from the left? Because if the limit exists, then the limit from the right, it should be the same as the limit from the left. So we have this theorem, the limit of the function when x approaching a. When we write this, ya shabab, x approaching a, it means from both, from the right and from the left. In general, this is in general. So the limit of the function when x approaching a will be L, if and only if, and this means that we have here double conclusion. Then also the limit from the left will be L, and also the limit from the right will be L. So in other words, you can write it like this: that when the limit of the function from the, let me write it here because I need the space for another one. When the limit from the right is the same as the limit from the left, when the limit from the right, this is from the right, and this is from the left. When they are the same, when they are equals, then the limit exists, and it will be equals to the value. For example, if these are equals to L, both of them are equals to L, then the function will be equals to L. So we can write it like this: the limit of the function when x approaching a, it is L, if and only if the limit from the right and the limit from the left are L also. In other words, this means that if the limits from the right and from the left are not equal, then the limit does not exist. The limit, when the limit exists, ya shabab, when we have a limit for any function, it should be unique. It should be one and only one limit. We cannot have two limits for one value of for one function. If that case happens, it means that the limit does not exist. At the end, eventually what will happen to the function should be one limit, not more than that. So the limit is unique. It is only one limit. Look at the previous example. Do you remember the previous example? What do you think in the previous example in the Heaviside function? Is the limit exist or not? When x approaching 0, when x approaching 0. When x approaching 0, the limit does not exist. Because when you are close from 0, what will be the limit? 1 or 0? Because you have only two values for the function, 0 or 1. So it is not there, so it does not exist. Shortly, we will write this with the 3 capital letters like this, D and E, which means does not exist. Why it does not exist, by the way? Because the limit from the left is 0 and from the right it is 1. So they are not equals. In that case, it is not. Okay, let me ask you a question, Shabab. What about the limit? What about the limit of the function of h of t, capital H? What is the limit of the Heaviside function when x approaching 1? What will be the limit? when let me make it 2 or 1, it doesn't matter. What is the limit of the Heaviside function when x approaching 2 يا شباب? From the right or from the left?
1.
It is 1. Or 3, the same. It will be 1. Because it is from the right or from the left, the same limit. Also, when you put it 3, it will be 1. For any a, so it will be when x approaching a, for any a greater than or equals equals 0. No, not at 0. At 0, it is 1. So it is okay. When a is greater than or equals 1, let's say 0. When x greater than or equals 0, the limit will be 1. And the limit for any x, for any a less than 0, it will be 0. The only problem, it is at 0. Sorry, this is cannot be greater than or equal 0. It should be greater than 0 strictly. So the problem is at 0. At 0, the limit is different from the right and from the left. For other points, there is no problem. Another example, ya shabab. I need to hear from you, ya shabab. Please, let me see what we can do. I'm presenting in the full screen mode, so it's okay. What is the limit? Let's take a shabab one by one, please. What is the limit of this function when x approaching 2 from the left? This is 2, x approaching 2. This is x, and this is 2. So we are talking about when x approaching 2 from the left. What will be the function?
Doesn't exist.
From the left.
3.
What we will do, go up, and look where is the function from the left. Here it is. So the function will approaching what?
3.
The value of y, it is 3.
3.
Yes, you're right. Now, what is the limit of g of x when x approaching 2 from the right?
1.
Go up or down, and look what is going to happen. It is 1. Now, what is the limit of the function? What is the limit of the function when g approaches 2?
D and E.
Does not exist.
Does not exist.
Exactly, it does not exist. Because why it does not exist? Because the two-sided limits are not equal. Now, what is the limit of the function when x approaches 5 from the left? So it is 2. So you already have seen it. So when x approaching 5 from the left, look at the graph. What is going on here? It is approaching what? 2. So it is 2. Now, when it is approaching 5 from the left, it is 2, and from the right, it is also 2.
Also 2.
So what we conclude from that? What is the limit of the function in general?
2.
It is also 2, because they should be, since they are equal, it is the value of the limit. Notice, ya shabab, that what is the value of the function at 5? What is
1.
g at 5? It is 1. Look, this is g at 5, which is 1. Oh, I think I have written that here. It is not 2. It is in fact 1. This function is not continuous at. Now, the third part of this section is the infinite limits. What we mean by the infinite limits? When x approaching a number from the right or from the left or in general, the value of the function will go to infinity. It will be infinity or negative infinity. This is the meaning of the infinite limits, when the limit is infinity. What we mean by that, and what does that mean? Okay. When you have a limit of like this, 1 over x squared, 1 over x squared. When x approaching what? 0. What will happen to this function? 1 over x squared. Now you can do it algebraically, numerically, by using a table of values, or you can do it algebraically, by the way, geometrically, if you know how to sketch the graph. But let me think about it easily, ya shabab. When x is so close from 0, مثلا, x is 0.001, let's say like this. You can add more zeros if you want. This in fact means what? 1 over 1000. Okay. Now, or indeed 1 over more than 1 over 10,000. If you did that and you square it now, this is x, and you will put it here, this is x, approximately طبعا. You put it here now, what you will have? You will have 1 over 1000 squared, which will be equals to 1000 squared. Okay, which will be of course 1 million. This means that when you have 1 over small number, it is important to realize that 1 over small number, this means that it will be what? It will go to infinity, positive or negative. You need to decide. Okay, is that correct? No. If you divide something by 1 over small number, it will be goes to infinity. Yes. Now the another one, when you divide 1 over big number, it will be close from 0. Okay, but let's focus on this case because this is the case that we need. It could be from the left or it could be from the right. So what we can write here, when you have 1 over positive small number, the limit will go to positive infinity. When you have 1 over negative small number, then it will go to what? To negative infinity. Very small, طبعا. We are talking about very small, very close from 0. We can write this, by the way, if you don't confuse the shabab, I can write it 0 plus. Also, this one you can write instead of that 0 minus. This means that it will be very close from 0, but positive. Here it means very close from 0, but less than 0, but negative. So now what do you think here? 1 over, is it going to be positive or negative? Because we have squared here. It will be over small number, but positive, because it is squared. So in that case, the limit will be positive infinity. We don't write positive infinity in general. So indeed, if you want to make a table, I don't advise you to use this case, but this is just for you to understand the meaning. Look at the graph, by the way. If you still remember the graph of this function from Math 101, here it is. This is the graph of 1 over x squared. It is not defined at 0. And look what happened when x approaching 0 from the right or from the left. The value of the function going where? It goes up and up. It increases without bound. So same in mathematical notation, we will write that the limit of 1 over x squared when x approaching 0 is equals to infinity. But be careful, Shabab. This does not mean that we consider infinity here as a number, because when you write equals, you should equal something exist and it is a number. It is not. In fact, the infinity is not a number. It is just a mathematical symbol. That means, I think I will explain this in the next slide. So also, it doesn't mean also, Shabab, that the limit exists. It is another way or specific way of the non-existence of limit. But of course, sometimes non-exist, the limit does not exist, but you don't know anything about it. Just you will say it does not exist. But here you know that it will get bigger and bigger and bigger. It will increase and increase without bound. So write it infinity when you know how it will behave. So again, the symbol infinity is not a number. Just we indicate that the value of x getting larger and larger, increasing without bound. This is the meaning of infinity, something that's getting bigger and bigger. So this is the definition of the infinite limit, the informal definition, of course. What we mean by that, it is explained here. It means that it will get larger and larger. Alternative notation, it is this. Look at this example here. When limit of the function is infinity, it means that the f of x becomes increasing function without bound. It will get bigger and bigger forever. So when x approaching a from the right or left, this is what you are going to have. What you will call it, this is the same if the limit is negative infinity. Negative infinity, it means that it will decrease forever. It will get, of course, down forever, the y values. It will be negative, big number, but negative. The value of it is negative. The value of it is big, very big, but of course it is negative, not positive. So this means that it will decrease. It should be mentioned here, yes, decrease. The function decrease without bound. It will keep decreasing forever. Like the function, if you have an example, negative 1 over x squared, just reflect this function on the x-axis. If you reflect it, you will have a function that the limit of it when x approaching 0, it will be negative infinity. These are some examples when x approaching a from the left, the function goes to infinity. Here, when it is approaching a from the right, it goes to positive infinity. Here, when x is going to approaching a from the left, the function goes to negative infinity. Here, when it is from the right, it is going to negative infinity. What you can notice, ya shabab, here, what we can say about the line here, x equals a. The vertical line x equals a is what? The vertical line x equals a is what? Vertical asymptote. Do you remember 001, chapter 3 and 001? Yes. This means that we have a vertical asymptote. So when we have vertical asymptote, we have a vertical asymptote x equals a if one of these limits happening. If the limit of the function is infinity or negative infinity, or if one of them is happening, or if it is from the left is infinity, or from the right is infinity, or negative infinity. So in short, if the limit of the function when x approaching a, or from the right, or from the left, equals to positive or negative infinity, in this case, if the one of these 6 cases happens, then we have a vertical asymptote at x equals a. For example, this function, the reciprocal function, do you remember it? 1 over x. 1 over x, when x approaching 0 from the right, it goes to positive infinity. When it is approaching 0 from the left, it goes to negative infinity. The y-axis, which is x equals 0, the y-axis is a vertical asymptote for this function. Usually, they are the zeros of the denominator at the simplification. When x approaching 3 from the right, what will happen to this function? And when it is from the left, what you can do here, you can just look at it in this way. Let me just explain the figure, but how can you do it? This is not difficult. We will see طبعا that, ya shabab, in I think section 2.5 with much easier methods. Now, when you think about numbers close from 3, here 3 from the right, like what? Like 3.1, for example. So it will be 2 times 3.1 over 3.1 minus 3, for example. So this, the denominator will be small, ya shabab. This will be fixed. It will be 6, for example, here, almost. And this will be very close from 0, but positive. So this means, I have explained it here. If x is close from 3, but larger than 3, then the denominator here will be positive. Why positive? Because this x, it is greater than 3. So what you will have here is positive. This will be positive. Here x is less than 3 because it is going from the left. So this expression will be what? Will be negative. It will be 0, almost 0, but negative. So it will be here some number over small positive number. So it will be positive infinity. Here you will have a number over a negative small number. So it will go to negative infinity. And this explains the limit of this function. طبعا we will learn a better way to do it when we divide by x. We will see that later. You can calculate this limit easily, like it will be 2 over 1 minus 3 over x when x goes to 3 from the left. And of course, in that case, you can calculate it when you have it this way. No, it is not this way. Sorry, it is not. This is when you have x goes to infinity, not this way. Just as I said, just think about when it is positive small number or negative small number. So we have x equals 3 here as a vertical asymptote. I need to specify the last 10 minutes, in fact, to explain some issues related to the course, but it's okay. We still have time. Let me explain how many examples we still have, ya shabab. Example 10, the vertical asymptote of the function tan x. You can do it in 2 methods. Did you know how to sketch the graph of tan of x? It will be much easier for you. Very easy. You remember how the graph of this function looks like. If you don't remember, remember that tan x, it is sine over cosine. And when x, the vertical asymptotes will be what? The zeros of what? The zeros of cosine. When cosine x equals 0, means that x equals what, Shabab? Do you remember? Pi over 2 plus n pi, where n is an integer. So these are the vertical asymptote of the tan. More explanation is here. And if you remember, this is the graph of this function. And these are all the vertical asymptotes. Pi over 2 plus n pi. Also, len x, look at the natural logarithmic function. It has a vertical asymptote at what? At 0. When x approaching 0 from the right, it goes to negative infinity. We don't know anything about it from the left, so the graph does not exist there. So we say that the limit of the len when x approaching 0 from the right,